Hello friends, in this video I'd like to show my solution to the following problem from the Nordic Mathematical Contest 1991, problem number 1. So we wish to find the last two digits of the number 2 to the 5th times plus 2 to the power of 5 to the second power plus 2 to the fifth cubed and so on plus 2 to the power of 5 to the power of 1991. Okay, so my hints for you for this problem. First of all, notice that we wish to find our sum modulo 100 because the last two digits are exactly the remainder of division by 100. And then it becomes a very standard problem which involves the Chinese remainder theorem and Euler's theorem. So give this problem a try and see you in a minute. Okay, so I hope that you tried your best. So first of all, by the Chinese remainder theorem, let's say that this sum is S. Finding S modulo 100 is somewhat equivalent to finding it modulo 4 and modulo 25. The first part is easy because S is congruent to 0 modulo 4 and it is obvious. Why? Because every number in this sum is divisible by 4. So this congruence is obvious. Okay, so the second part is not so obvious. Finding S modulo 25 by Euler's theorem. By Euler's theorem, we know that 2 to the power of 5 to the power of k is congruent to 2 to the power of 5 to the power of k modulo phi of 25 modulo 25. Okay, what is phi of 25? Phi of 25 is 25 minus 5, 20. Again, if you don't know what's going on here, check what is the famous Euler phi function on Wikipedia or other sources. Okay, I assume that you know something about this function. If you don't, check Wikipedia, for example. Okay. So we know that this is congruent to 2 to the power of 5 to the power of k modulo 20 in the exponent modulo 25. And now to go forward, we have to simplify 5 to the power of k modulo 20. So let's do exactly that. Again, by the Chinese remainder theorem, 5 to the power of k modulo 20 is somewhat equivalent to finding it modulo 4 and finding it modulo 5. Okay. First of all, what is 5 to the power of k modulo 4? Well, 5 is congruent to 1, so our number is congruent to 1 modulo 4, and obvious, it's congruent to 0 modulo 5 for positive k, or k which is a positive integer. Okay, but now by the Chinese remainder theorem, we know that there is exactly one number between 0 and 20, which is both congruent to 1 modulo 4 and congruent to 0 modulo 5. It's pretty easy to check that this number is 5 itself. 5 itself. Okay, very nice. So now our sum, which was the sum over k from 1 to 1991 of 2 to the power of 5 to the power of k. Now we know that this sum is congruent to this sum 2 to the power of 5. So we have 1991 times 33 modulo 25. Okay, but now let's simplify it. 1991 is congruent to minus 9, and 32 is congruent to 7. So this number is congruent to minus 63, and minus 63 is congruent to 12 modulo 25. Okay, and now finally the last part. We have established that our sum is congruent to 0 modulo 4, and our sum is congruent to 12 modulo 25. Now, again, by the Chinese remainder theorem, I feel that I'm repeating myself, there is exactly one number between 0 and 100 such that it's congruent to 0 modulo 4 and congruent to 12 modulo 25. And that number is 12 itself. It's pretty easy to see. So we have our answer. The last two digits of our number is 1 and 2. So our number ends in the digits 1 and 2. Okay, so I hope that you learned something new. I hope that you enjoyed this video. See you next time. Thank you for watching and goodbye.